Hi everyone, this is Zhang. I'm going to present our interspeech paper, an empirical study on channel effects for synthetic voice spoofing countermeasure systems. Our research topic belongs to voice biometrics. We know that voice can be used to verify the identity of a speaker, and this system is called automatic speaker verification, or ASV. We usually expect that the input of this ASV system is bona fide speech. In other words, natural speech produced by humans. However, this ASV system could be vulnerable to spoofing attacks. The spoofing attacks include impersonation, replay, text-to-speech, and voice conversion attacks. So here comes another standalone system, spoofing countermeasure system, also called anti-spoofing, which aims to detect spoofing attacks for speaker verification systems. In common settings of anti-spoofing, according to the ASVspoof challenge, LA attacks refer to text-to-speech and voice conversion algorithms, or combinations of them. These attacks contain algorithm-related artifacts. PA attacks refer to replay attacks, which have device-related artifacts. Our current focus is to detect LA attacks. Above are some introduction of the research topic, voice anti-spoofing. About our paper, I'm going to introduce the following parts: background, cross-dataset studies, channel robust strategies, and our conclusions. The background is that most work develop a well-performed CM system on a single dataset, where they train and test their system on different portions of the same dataset. Several cross-dataset studies show significant performance degradation. They train the system on LA datasets, but test on PA dataset. The degradation is reasonable since the artifacts are different in two kinds of attacks. However, some cross-dataset studies show performance degradation across different LA attacks, and we try to analyze the reason for that. Recent studies show that the reason for performance degradation is that different datasets contains different attacks. The new attack algorithms could be more difficult, and they are unseen during training. However, we propose that other differences could also contribute to the performance degradation, such as channel variation. We believe that there are limited channel effects presented in the training set, so the CM system may fail to generalize to unseen channel variation. This is our motivation to investigate the channel effects for synthetic voice countermeasure systems. Here, channel effects refer to audio effects imposed onto the speech signal throughout the entire recording and transmission process, including reverberation of recording environments, frequency responses of recording devices, and compression algorithms in telecommunication. The next part is our cross-dataset studies. We first conduct a cross-dataset study between three logical access datasets. The first is ASVspoof2019 LA, which is from the ASVspoof2019 challenge. It contains 6 attacks for training and 13 other attacks for evaluation. Next is ASVspoof2015. It contains 5 attacks for training and includes 5 other attacks in the evaluation. The last one is VCC2020, which is a dataset from Voice Conversion Challenge 2020. We use this dataset as evaluation data and consider their training data as bona fide speech and the submitted voice conversion results as spoofing attacks. We employ 3 state-of-the-art CM systems for the cross-dataset study: LCNN, ResNet, and ResNet with one-class learning. We observe significant ER degradation on all CM systems. We then plot the score distribution of spoofing attacks and bona fide speech to analyze why the ER degrades. From the figure, the score distribution of bona fide trials shifts down significantly from ASVspoof 2019 LA to ASVspoof 2015 and VCC 2020. This suggests that the main cause of the ER degradation is some differences in bona fide speech, among which channel variation is worth checking. To check the channel mismatch issue, we compared the average magnitude spectra across all bona fide utterances among these three datasets and observed significant mismatches. With this observation, we hypothesize that the channel effects mismatch between the three datasets is an important reason for the ER degradation. We then conduct a controlled cross-channel experiment by training the three SAM systems on ASVspoof 2019 LA and evaluating them on the evaluation set of its channel augmented version, ASVspoof 2019 LA SIM, which is generated by passing ASVspoof 2019 LA utterances through an acoustic simulator. From the results on channel augmented data, we observed that the average ER dropped significantly from ASVspoof 2019 LA, and the standard deviation is quite large. We conclude that the channel mismatch between training and evaluation is indeed an important reason for the performance degradation. The next part is channel robust strategies. We propose three channel robust strategies: augmentation, multitask augmentation, and adversarial augmentation. Augmentation uses the same model architecture as the vanilla model, but is trained on channel augmented data. Multitask augmentation adds a channel classifier to the vanilla model architecture to form a multitask setup. Adversarial augmentation inserts a gradient reversal layer between the embedding network and the channel classifier. For the training objectives of the proposed training strategies, we minimize the classification error of the SAM classifier for the vanilla and augmentation methods. For multitask augmentation, we train the three parts together and minimize not only the SAM classification error, but also the channel classification error. For adversarial augmentation, the embedding network aims to maximize the channel classification error, while the channel classifier aims to minimize it, forming an adversarial training paradigm. So the learned speech embedding would be channel agnostic and make the SAM classifier more robust to channel variation. For in-domain test, we evaluate the proposed strategies on the evaluation set of our simulated ASVspoof 2019 LA SIM dataset. From the result, we can see that the average ER on SIM channels and the ERs on unseen channels of all three training strategies decrease much from the vanilla model. The standard deviation of the ER across the 10 SIM channels also decreases. This shows that the proposed strategies do improve the channel robustness of the SAM system. We then perform a cross-dataset evaluation with the three datasets. Results show significant improvement on both out-of-domain datasets, ASVspoof 2015 and VCC 2020. We plot the new score distribution, and we observe that the score distributions of spoofing attacks are not changed much, while those of bona fide trials in ASVspoof 2015 and VCC 2020 are all moved up. This suggests that the channel mismatch issue mainly resides on bona fide speech, and the proposed strategies are useful. Finally, about our conclusions. The channel mismatch between training and evaluation is indeed an important reason for the performance degradation of CM systems. Our proposed several strategies, data augmentation, multitask learning, adversarial learning, improve the robustness of CM systems to channel variation. Thank you everyone for your attention. If you have any questions, feel free to send me emails.